the Q&A function. So send us any questions you've got. We'll feed them in as we need. On a co-host, Chloe Coppett is one of Exergy's certified energy professionals, and she's actually going to run this show just because I have a tendency to be just way too wordy. So again, thank you so much. And Chloe, I'm going to turn it over to you.
Awesome. Thanks, Dave. Well, I really look forward to getting to learn more from you guys and along with the audience. So if you don't mind, I'll just get right into it. How's that sound?
Let's start off with some introductions. So let's start with you, Bob, there.
So, yeah, Bob Long, I'm the founder of OHX and basically the inventor of the thermal energy battery. Many years in industrial refrigeration, too many in fact, but hopefully that's what's underpinned this technology to make it successful.
Okay, given that accent, I don't think we're in Brooklyn here. So where are you guys calling in from?
So we're in the northwest of England.
Great place for refrigeration. Thanks, Bob. David.
Yeah, hi, I'm David Grundy. I've worked with Bob for more years than I care to remember on various projects. Bob's an engineer, as is Jeff. Jeff will explain himself. I'm the non-engineer on the team, so I tend to look after everything non-engineering, particularly in financial and commercial matters. So if it's a technical question, I'll be keeping quiet.
And Jeff.
I'm Jeff Barker. I'm a chartered mechanical engineer. I've been working with Bob and David now for a few years on this project. Been involved in sort of alternative and clean energy technologies for probably the best part of, well, nearly 30 years. Maybe 6 or 7 different startups, so quite familiar with the challenges of early stage energy related businesses.
Chloe, over to you.
Great. Yeah. Well, I really appreciate the introduction. You know, I think a lot of us on this call know that ice storage has been around for a very long time, and it is a well-established technology. However, in speaking with a large number of facility managers and building owners, we've actually been surprised at the large percentage that are unaware of it. So I was curious if you could provide our listeners with sort of an introduction and a background on thermal ice storage.
Certainly, as you say quite rightly, ice storage has been around for many years, not least the years where sailing ships used to go and take block ice from the Arctic cap and bring it back before refrigeration of today had been actually invented. In 1945 and onwards, the dairy industry were great users of ice bank technology. It fitted their working day. They had cattle out in the field every 10 or 12 hours. They needed to be milked, and that's when the heat load appeared. So it made a lot of economic sense and practical sense to build an ice bank over a 12-hour period and deplete it during maybe a 2-hour milk cooling session. The reason that ice bank technology hasn't grown, I personally feel that it was limited in its malleability. It fitted quite well into a handful of niche markets, and beyond that, it generally displayed too great a footprint, lack of finite control, and not always displaying the economics one would expect.
Right. Yeah, that's it's really interesting. That was kind of my next thought was, what are some of the problems and restrictions of, you know, maybe the current before organic ice storage technology? And I'm assuming that's probably the largest issue, that it's not malleable. Would you guys say there's any other limitations that haven't been addressed yet that maybe, you know, your technology is starting to address with market?
In our emerging world looking after renewables, that has thrown up other limitations of ice bank storage, in that when the energy delivery is of a peaky nature, and say wind turbines and solar, that tend to deliver when they feel like it rather than when the client needs the energy. You find that there's a lot of energy available in a short period of time. And existing ice bank technology can't capitalize upon that because it can't bank the ice material fast enough to take advantage of the low tariff. Similarly, if you have a factory that has got high load peaks, you have trouble in discharging the battery in enough time to provide the support that's necessary.
Yeah, definitely. I think in the US we see that there's two camps, so to speak, that are both quite committed. And on one side it's ice storage and the other is chilled water. I guess I was curious when I was kind of doing my own research, what necessarily is behind this argument. Is that something that you guys see elsewhere outside the US, or just kind of curious your thought on that aspect of it?
We don't consider chilled water as an energy storage medium. It's particularly effective. I can understand why it entered the market in the absence of Organic Heat Exchanger's Energy Vault. And indeed, the growth in that market, although limited, only added to our confidence that our commercial market is extremely large.
Mm-hmm. And so to my understanding, ice, obviously can store more heat due to the latent energy. But and ice is well known as a great storer of latent heat, but also poor thermal conductivity. How does your technology specifically address this? I know we kind of spoke on this partially already, but just more in depth, I guess.
Yeah, I'm going to hand over to Jeff on this one. He's done quite extensive work and produced the diagram you see on the screen now. So over to you, Jeff.
Yeah, I think there are two ways to answer that. The water question first, and then how Energy Vault delivers that high energy density. As you say, ice has got a high thermal conductivity, but the ice particles in Energy Vault are basically tenths of a millimeter in size compared to solid ice on a pipe. But just to answer the question about water, this diagram sort of tries to illustrate the difference, really. And as you rightly say, most of the energy is stored in latent heat in ice. And we had this question actually from a colleague not too long ago. Somebody had asked him the same question. In the UK, sometimes you see cold water storage as a buffer storage, for instance, in a data center, but it's a small quantity of storage. It's not there for energy management at all, and so it's a relatively modest amount. So you wouldn't really call it energy storage as such, more of a buffer. But if you want to compare, a megawatt hour of coal storage, for example, which this sort of illustration does, basically you need significantly more footprint and volume of water. And of course, with ice storage, you're depleting the ice, delivering that cooling at a constant temperature, because as most people on this call know, you're going to basically melt that ice at a constant temperature. Whereas with a water system, you got central heat. It's changing temperature all the time, which is the reason why this is illustrated as five sequential tanks, because you're trying to avoid that stratification that if you had one very large tank that would occur. So to try and maintain a low temperature out into the plate heat exchanger to support a chiller, as in the illustration, then you probably need some kind of cascaded multiple tank system in order to maintain consistent flow temperature into that heat exchanger. Whereas in an ice storage system, generally speaking, you would be taking that water off at a constant temperature without having to try, because it's basically melting at the same temperature. The other point, Energy Vault, and we haven't sort of described the key principle and big difference here, is that Energy Vault produces an ice slurry. And again, people will have heard of binary ice and other similar sort of terms used for granular ice. And the background to this is actually the technology that Bob developed. As you mentioned, he's the inventor of this technology, which relates to using this type of system on board trawlers for producing an ice slurry, basically refrigerating and crystallizing seawater. And what this technology does effectively is produce tiny ice particles, maybe a tenth of a millimeter thick, that are effectively small round ice particles with a very, very high energy density. But also, because of the nature of the spherical peaks of ice, you have this 66 2/3 concentration of ice against the liquid. And because of this spherical nature of it, you always have a path of fluid between these various particles. So the surface area is absolutely colossal in comparison to a more conventional solid ice system. So you have this ability to release that energy very rapidly. And I think when we spoke to David initially, I think he got it straight away that, you know, basically you could respond very, very quickly to a cooling demand, or you could respond very, very quickly to switching a chiller off and maintaining the cooling basically seamlessly as far as the demand was concerned, which you simply can't do with a solid ice system. And I think that's probably they're the big differences effectively. I don't know if you want to add anything to that, Bob?
No, I think you've covered that quite extensively there, Jeff. Yeah.
Let me ask a couple questions here, Jeff. First one, just because appreciate the diagram there, but can you give me an idea of the difference between just the volume or the size of chilled water versus Energy Vault? So you had like five containers there. What am I talking about size-wise?
Yeah, David, do you want to just pop that diagram back up there, because I can't remember the number off the top of my head, but it is on the diagram. Yeah, so you can see there, I think each of those cylinders is about 10,000 or about 10 meter cubed. Sorry, it's not in your imperial numbers, about 10,600 litres. So there's about a total of 53,000 litres of water to deliver the same equivalent as an Energy Vault, which would be, what's the volume there? Probably about 12,000. So it's about a quarter of the volume, maybe less than a quarter of the volume of a water-based system.
Great, thank you. I appreciate that. The reason for the slurry is really about the discharge time, right? Because that was the biggest problem, you know.
I think you could look at it. You could look at it from both angles. You look at it from the charging angle and the discharging angle, because solid ice systems tend to be become less and less efficient as they grow the ice on the pipe, because you're increasing that insulating barrier between the fluid you're trying to freeze and the cold fluid inside, whether it be a glycol or direct refrigerant. But obviously on the discharge side, you know, you've got a considerably higher surface area from which you can deliver that cooling. Bob, you wanted to jump in there, I think.
Yeah, the whole manufacturing process relies upon an absolutely clean surface area. So what we are actually producing the ice crystals on is the internal of a wiped surface heat exchanger, where the parent fluid is pumped through a refrigerated cylinder. On the wall, normal dendritic ice crystals will form in their embryo stage. Before they've actually had the time to form fully, they're wiped away by a Teflon wiper blade and then trained in the body of the flowing parent fluid. In doing so, it means that there is no insulating barrier between the forming ice and the heat exchange surface, which means that our apparatus can run at a much higher coefficient of performance than its ice bank counterpart, that starts off quite efficiently, and then as the ice bank nears completion, the thermal transfer is so limited through the insulation effect of the ice that the efficiency starts to plummet in a bad way.
So nerding out with you for a second, Bob. Sorry, Clay, I'm on the nerdy questions here. Okay. In the US, and you know, we've seen ice banks essentially run the chiller at a lot lower temperature, like, you know, like 27 degrees or so at night, make the ice, et cetera, et cetera. Those chillers suffer a fairly significant efficiency loss and their COP drops dramatically. What's the difference between making ice with your, I think you call it a charger, and its COP relative to making it with the chiller itself?
In all honesty, not so boastful, because we like to crystallize our ice around -12 to -14 degrees Celsius. Which in Fahrenheit is going to be around 4, 5, I guess. I'm not my comparator here. The upshot is that our equipment is unlikely to run with a higher COP than a well-found chiller. the comparison isn't strictly that simple. If you have only got 27 degrees Fahrenheit, you've got what, 5 degrees of frost there, which means that the temperature differential over your ice maker or your ice making surface is exceptionally low. And at that, you would need a colossal surface area to build any ice. So footprint is probably going to be the deciding factor there as to whether it's efficient to run the chiller or to have a third-party manufacturing source. I can understand the motivation in that you've got the capital equipment there, and you can probably run it at night and rather than on demand through the day. But when you look at the feasibility of it and the surface area you would require and the thermal losses that that surface area represents, that would probably bring the coefficient of performance down quite significantly, but very difficult to quantify.
Thanks, Bob.
Yeah, that so just listening to you guys talk about all of that, this all of course sounds very new. So I was curious, is there any commentary on the technology risk side of things, or has that not been an issue that you guys are concerned with yet? Or, with regards to how the system is controlled, is there a technology risk with this new type of product, so to speak?
That's quite an easy question to answer from our side, in that the Energy Vault, that is the store for OHX's product, is basically an inanimate, heavily insulated container.
Mm-hmm.
What we do from there is we pump the clear water not containing ice from the bottom of the container around the workpiece, the plate heat exchanger, the produce cooler, or whatever, and then back to the top of the battery to be cooled by the phase change material in the battery. So in itself, it doesn't represent any major technical leap of faith. On the charger side, things get a little more complicated, but to underpin the technological stability of the charger, my company has been making these since 1995 for the marine industry to turn seawater into a slurry for the preservation of expensive catches, called majority in tropical waters. So the arduous of a marine life and the hard environment, the harsh environment it represents, has meant that the development of these machines over the last 35, 40 years has honed them into a fairly tolerant piece of equipment that we have little to no technical concerns putting them out there commercially.
Yeah, that's awesome. I think it sounds both complicated and, intrusive regarding the control of someone's chiller, so to speak. How would that affect, so say, my chiller operation in terms of the operational, the service, the maintenance, and the warranty side of things?
On your chiller, there would be no negative impact on warranty liabilities, simply because we bury our system completely from your chiller. The only interface is purely a thermal one.
Got it.
Plate heat exchanger generally, and a fairly inanimate block. On the chiller side, maintenance, that will continue as previous. The running of the chillers will continue as previous, but in this day and age, I would imagine that a chiller system would be attached in some way to a building management system. And our equipment has been built to take instruction directly from the building management system. So depending on the level of intelligence of the system, it may or may not decide when energy tariffs are too high to actually pay. And then it would be instrumental in winding down the chiller and allowing the Energy Vault to take the load. And that would be a seamless operation. driven primarily by temperature. So if your chillers were seeking an export temperature of, let's say, 40 degrees Fahrenheit and anticipating a return temperature of some 48 degrees Fahrenheit, that would continue. If the BMS decided to truncate the operation of one chiller, the anticipation would be that that 40 degrees would rise to maybe 40.5 degrees. At that point, the energy vault can be engineered to start sending incremental energy in response to that small temperature rise. So there are many, many ways to integrate. If the client doesn't have sophisticated integration, we also have an artificial intelligence package, which we can offer as an addition.
Yeah, that's awesome. You know, in the US, there's been a big push lately, especially in larger cities with a ton of buildings, such as New York, for example, about reducing our carbon footprint. So with regards to your product, you know, I'm sure it's more than just a quick sentence, but how does your product save your customers, or I'm sorry, help reduce your customers' carbon footprint specifically?
Yeah, it's gone in a financial direction, so I'm going to hand it over to David.
Yeah, thanks, Chloe. It's quite interesting what the customers' reactions has been to Energy Vault, because it does, and we'll explain how it does help save carbon. But when we started the development of it, we very much thought people would be interested in the economic return from an Energy Vault. So how much money could we save them fundamentally? And actually talking to customers in the UK and now overseas, there's probably as much interest in the carbon savings as there is in the economics. And that dynamic has probably changed in the last probably 2 or 3 years, even if not 4 or 5 years. But they all come back to the same approach. They're like anything else, we're a battery. So we store energy. And what we do is we can store energy when carbon intensity is quite low. So we can optimize the system for economic savings, or we can optimize the system for carbon savings. So with the software that we've got, you can charge through solar if you've got solar in your factory, or wind, or if you know that the grid electricity is low carbon, you can charge the Energy Vault then. And you can discharge the Energy Vault when carbon intensity is high on the grid. So you can switch off using high carbon electricity and use the energy stored in the battery. So actually, you know, typically the economic and the carbon impact of that is pretty much the same time. Sometimes it varies a bit, but if electricity prices are high, it tends to mean there's high carbon intensity. If they're low carbon intensity. And the way that we've done this, I'll just show a slide. So
if I could interject here just a second. I think I put a slide up. Can everybody see it's a map?
Yep.
Is that up? So just for the audience, these are the states and cities in the United States that are now mandating carbon footprint reporting, energy intensity reporting, benchmarking, and things like that. And you'll see it's most of the major cities in the US. So David, that's one of the reasons why they always come down to economics, but right now they're really facing carbon footprint issues. And in most cases, there are penalties if they exceed a certain degree of, carbon, footprint for the type of building they have. So I just thought I'd share that it's a big and growing market in the United States.
Yeah, absolutely, Dave. And that's the part of that is some of the designs that we've built into Energy Vault, which I think are probably just worth just sharing. Just let me pull up another slide. So the first thing to say, Energy Vault's been designed with huge flexibility. So it's a modular system. So we have the basic system is a 1 megawatt hour storage tank. We have the battery charger that Bob's explained, and then the interface heat exchanger that links our system to the customer's systems. And these can be configured and built up in different numbers of charges and different numbers of tanks, depending exactly what the customer wants. So if you want very fast charge, very slow charge, very fast discharge, very slow discharge, that can be done with Energy Vault. So the system can be designed to maximize economics or maximize carbon savings, just by building different variations of the numbers of chargers and the number of tanks. A lot of people are using electrical battery to help them manage their electrical inputs and save carbon that way. And we do something very similar, but about half the price of an electrical battery. So, what we've got is a tool, and it is no more than a tool. It's a tool that allows customers to use Energy Vault in the most efficient way for their operations.
Yeah, and I guess kind of backtracking towards the chargers, I know that traditionally in the US, ice storage, we use the standard chiller, and it just ran much colder, typically in the 27 to 29 degrees Fahrenheit area to, make ice. So I'm curious, how much efficiency loss occurs with this, and how does your charger that you were referring to address that issue?
The charger, as I was saying before, because of the temperature band it operates in, is unlikely to beat the coefficient of performance of a standard chiller. However, what it can do that the chiller can't is source its energy very cheaply. So if you have energy that's probably 20% of its normal peak demand value, and you use the charger to access that energy, then the coefficient of performance becomes less important.
Okay.
So if you charge the bank with energy at a fifth of its normal cost, but at 80% of the efficiency of a chiller, you are still on aggregate saving.
Yeah, I'd like to explore that a little bit, Bob, from the perspective of you essentially using a wiped film heat exchanger or ice maker here, essentially, right? You're doing essentially small crystal growth, wiping it off. So I'm going to say coefficient of performance, but your efficiency is basically constant through the entire charging process, so I would assume, right? Because we're not getting a buildup of ice. Whereas the COP of a chiller might be relatively good, but the efficiency is not, because as the ice builds up, and it builds up from the coil out, the heat transfer goes down. There's that insulating layer. Ice is not a good heat transfer. So it actually is much less efficient in building the ice over time, where yours is almost, am I correct in that, Jeff? I'm sorry, Bob?
Efficiency and COP in this particular context are probably different focuses. Why I say that our COP is lower is simply that we are operating around the 4-degree mark, not the 27-degree mark. So the relevant relating COP to our refrigeration equipment will be lower than the chiller. If you take that chiller into ice building scenario, then I would probably argue that 27, 29 degrees isn't a low enough temperature to be effective. Which again will bring the chiller's COP down. So it's quite a complicated comparison with many factors changing as the ice bank builds. But as I say, the main limitation that I see is that you need a protracted time factor to use your water chiller, whereas with the Energy Vault charger, you would have purchased the charging mechanism to match your charge profile after investigation.
Yeah, if I could just pick another point from what you said there, Dave, you mentioned that the Energy Vault charges up on a consistent basis over a period of time, so often overnight, and it does, and that means that our COP is quite consistent and it's quite an efficient system because it's constantly going. what we're finding with a lot of customers we're talking to is their chillers are cycling on, off quite regularly, and that makes them inefficient. So one of the benefits of Energy Vault is you can stop that on-off cycling of your core chillers, operate a chiller at 100% efficiency or zero and switch it off, and use Energy Vault to smooth that on-off profiling, which can materially make quite a big saving.
Yeah, just to jump in there, the demonstration site that we've been recently running on a pharmaceutical plant in the northeast of the UK has demonstrated. I mean, obviously, the climate is slightly different in the northeast of the UK, but I'm sure there are similar ones elsewhere in the US. But basically, what we were seeing was, COPs of the chillers cycling on and off on part load to deliver, a small proportion of the capacity of the chiller. Which effectively meant the COP was below 2. And so the comparison with the COP of the Energy Vault and its charger meant that just by simply replacing that chiller duty with Energy Vault, you were immediately reducing your energy consumption and reducing the associated carbon emissions equivalent for that energy you've replaced. So as David was saying, for large parts of operation where those chillers are effectively cycling, short cycling and at part load, you can demonstrate considerable energy and carbon savings by delivering that cooling with Energy Vault.
So something else that we've noted from carrying out surveys on clients is that it's not always good to believe the coefficient of performance printed by the chiller manufacturer.
Right. Yeah, so I guess for my understanding, so by incorporating Energy Vault, is it possible to reduce the number of or size of chillers I need overall, or is that just with regards to the off and on cycling?
You can reduce the size of the chillers. Your heat load will always remain your heat load. So if you're under capacity, you will still always be under capacity. And we see Energy Vault as an addition to the load, not to handle part of the load at the time of purchase, because it's a banking technology you're buying. If it's essential to bring it into play to handle the load, then you will probably restrict the banking periods available. Got it.
I guess for someone like me, it's hard to picture how big the unit is, and is it complicated to install for customers, or is it something that is relatively easy, from an engineering perspective, I guess?
The Energy Vault is basically a skid mount delivery package. The Energy Vault engine room, unless the client is providing a machinery space, would be in a half-size 20-foot container. The Energy Vault itself is actually constructed within a 20-foot container. That's done for a number of reasons. One, obviously, the free availability of these receptacles, but secondly, so that we can multiplex with some form of unity.
Oh, awesome.
I think I put a picture up, gentlemen, of, I think, both the charger and the Vault itself on your screen.
Yeah,
that's correct. Yes, the Vault is undergoing some fairly radical redesign changes to create more volume within the same receptacle. The charger is pretty well going to remain the same. You see on the bottom line there are 4 horizontal crystallizers. They're fitted in a handed manner. So on the first one, you will see a blank end. The second one, you will see the reduction gearbox. The third one, a blank end. The fourth one, a reduction gearbox. If you were to go to the other end of the unit, you would see the other 2 gearboxes.
So that looks fairly small. So
yeah,
I'd say it's about sort of 1.6 meters wide by 2.5 meters long, something like that.
That's it. Yeah,
maybe by about 1.8 meters high. So it sits within a standard ISOFreight container.
So we've got a question. It says, does it only work with salt water? So I think they're right. So Bob, I'm going to throw that one to you, Bob.
Yeah, no, we only use salt water in the marine environment. Our chosen fluid is a product over here in the UK called Blended, and it's a polypropylene-based glycol with a biocide in it. Everything is to food grade, but we like it because the actual temperature depressant used creates a very, very small crystal. The smaller the crystal, the higher our surface area, and our whole rapid charge is built upon the availability of surface area.
So
David,
also your system, let's say the fluids, the heat transfer from your system never touches directly that from the chiller. There's always the heat exchanger in between. But does the mixture, the glycol plus the water, reduce the freezing temperature of the water?
Yes, we crystallize at -2.5 for general air conditioning chilled water support. If we're supporting a low temperature application, we can crystallize anywhere down to -30. But those were specialized applications that would be taken one at a time. Our bulk market is crystallizing at -2.5, 2.8, and supporting the chilled water market.
So that means that our side of the system, we can tune the fluid crystallization temperature relative to the chilled water circuit on the client side. So David, do you want to put the general schematic up, David? Perhaps we can just describe, I know it's been up on the screen once already, but we could just perhaps reinforce that point that Bob's just made. Yeah, so
talk them through that, Jeff.
So yeah, you can see like a vertical dotted line, the left-hand side of which is the energy vault side, which includes that interface plate heat exchanger. The pictures you just saw of the physical unit, the thermal battery is obviously, as Bob's described, is the store, the 1 megawatt hour element, and the thermal energy battery, the more complex mechanical refrigeration piece of equipment. Associated with that is a small cooling tower to provide the condensing. But obviously, well, part of the system also allows for heat recovery. So the design of the thermal battery also allows for high temperature heat recovery through a desuperheater off the discharge of the compressor, and lower temperature heating from the condensing water. So there is also, although it's not shown on this diagram, the opportunity to take that thermal energy out and recover that. Obviously, on the right-hand side of that dotted line is the client side. So effectively, that's circulating cold water circuit with 1, 2, or 3, or however many chillers in cascade, providing the normal cooling duty to the demand point. What you'll see, so effectively we decouple the energy vault circuit from the chilled water circuit of the client. That allows us to tune, as I already mentioned, the crystallization temperature on the thermal battery, which may be different to whatever glycol concentration is in the chilled water circuit on the client side. And we can simply control it via a three-way valve. So that, as Bob's mentioned, is connected to the BMS. The BMS may trigger the support required from Energy Vault, and essentially it opens a modulating valve which controls the flow of cold water out of the Energy Vault at -3 degrees consistently, in order to maintain the temperature flowing off the heat exchanger into the client's demand. So that control can deliver, 1 kilowatt or 1,000 kilowatts. So it's able to support quite a wide range of varying demand requirements. And I think, as we've already mentioned, depending on the time of year, we're finding in the UK, for instance, where the short cycling compressors can be switched off essentially for long periods, you can allow the Energy Vault to provide most of the duty. In this particular application, we mentioned the pharmaceutical plant. During the summer, they have particular deficiencies on the chillers, in which case Energy Vault will be providing short duration peak cooling to support the chillers. So the chillers will be coming on 1, 2, 3, and Energy Vault will be supporting the peak load. So it varies depending on the climate and across the year, effectively. So you can deliver chiller efficiency improvements during the shoulders of the year when they're part loaded and cycling on and off, or you can deliver daily short peak duty. We've spoken to a number of food manufacturers in the UK, some of which, and pharmaceutical manufacturers, a range of them often have short duration peak process cooling, which may be an hour or so once or twice a day. So that Energy Vault enables enables you to deliver that that peak cooling pretty much instantly. And back to the point I think you mentioned, Chloe, a little while ago about whether you could reduce your chillers. Certainly, if you were designing a new system, you could say, okay, I will design the system for base load, and if we have short-term predictable peaks, use the storage mechanism for delivering the peaks. So depending on the application and the duty cycle, you can tune the system accordingly, whether it be retrofit or whether it be new build.
Yeah,
we're getting some great questions, and the reason we're calling these great questions because they're questions that are very serious about the technology. So one of those is obviously people planning on doing this or so. What's the weight per container? Because again, we think of this as going into buildings in a city and things like that. So there are obvious concern about that. And then also, what's the largest building that you've currently installed in, or your largest installation to date?
The largest installation to date is the Quotient Scientific installation that is currently producing all the test figures. That has an 800 kilowatt store. I mentioned earlier we're redesigning the store to hold more energy. So our 1 megawatt store will be represented by a 20-foot container.
And around about 20 metric tons, 20,000 litres of what?
22 tons weight.
So the 20 metric tons, that's for, I'll call it the Energy Vault, the battery itself, because that's primarily whatever 1,000 gallons of stuff, right? What about the charger? Is that included in that weight?
No. The charger is weighing in at about 450 kgs.
Okay, so not very much. Since we're getting questions like, size, location, that type of thing, just to help people to understand whether they're a good fit or not, how would you describe your ideal customer profile? Who should really, really just say, I look like these guys, I should do this?
Anybody with a chilled water system that wants to economize it. Certainly the people that are even considering storing chilled water wouldn't be there if they didn't have a large footprint to offer. So, we would probably be 4 or 5 times less footprint for any given storage. The other thing, of course, is we don't really have that many comparisons because our battery can discharge 0.5 megawatt for 2 hours. And I don't know of an ice bank, a conventional ice bank, that it can even come close to that sort of discharge rate, which means that for a relatively small investment, you can support colossal size apparatus for not a lot of money.
Yeah, I think one of the things that we've referred to for clients here is that systems that have got probably chillers in excess of 200 kilowatts. So that's the sort of scale. Anything above that is likely to have to see a benefit from an Energy Vault being attached. An Energy Vault, can be scaled up and down from the sort of general figures that we've talked about from a modular point of view. So maybe from 0.5 megawatt hour through to 1 megawatt hour and multiples thereof.
Yeah, just for Exergy customers, we are super interested in this technology and deploying it not only for, again, energy savings, cost savings, carbon footprint, but for things like demand response, especially in cities during the summertime. This battery is unique because it's a rapid discharge, which allows us to do things like demand response at its most economical level versus standard ice banks sort of discharge at the same rate as they charge, which is just long and slow and things like this. This is a very unique development.
Yeah, I'd say that the discharge is probably at least 20 times the charge rate. So there is a big ratio there, and that's the one of the key unique features, and obviously based around the fact that you've got a nice slurry with a colossal surface area. It allows you to release that sort of stored latent energy very rapidly and at a constant temperature. So again, it addresses the questions of water storage and conventional ice bank, and offers benefits that neither of the other two can deliver.
Okay, we got another question here. How long does it take to charge, to build up the capacity to discharge for 2 hours? And I guess that depends, of course, on what your discharge rate is, but what's the charge rate versus the discharge rate?
If you have a 1 megawatt hour battery and a 100 kilowatt charger, it will take you 10 hours to charge the battery. And if you want to discharge it in half an hour and support a 2 megawatt load, theoretically you can.
Yeah, Dave,
Wow.
I think that's picking up my point from earlier. Because it's modular, you can have different combinations of chargers and stores. So you can put multiple chargers together and then fully charge the 1 megawatt hour store pretty quickly. But there's another model where it is almost an insurance backup for cooling system downtime. We could have one charger and perhaps 2 or 3 stores that might take, over a day to fully charge all the stores, but then that stores there available for your emergency protection. So it's very hard to say exactly what the charge time is because it's flexible to the modularity of the system.
The other thing to consider is for essential services, there's another scenario comes into play. If we take perhaps a data center example, they've got 500 kilowatts of cooling, they have a standby generator, the process is relentless, the power goes out. They only need 15 minutes support to get the generators online, etc., but the cooling must prevail. The Energy Vault will provide that 15 minutes at half a megawatt cooling potential without any problem at all. But the background benefit would be in owning an Energy Vault, they would, under normal non-power out circumstances, be able to economize the operation of their in-house equipment. So it hits at 2 levels. Where you've got essential services that must be maintained, it can deliver colossal output for short periods to maintain a large plant, but it can earn its keep in between those eventualities just by optimizing, managing, and economizing.
I think the term Bob's used for some people is like a thermal UPS, because UPS systems are obviously ever present in a data center, but they're not there to support the cooling load. So the thermal UPS, such as Energy Vault, would deliver that, fill that gap effectively, allow you to operate the computing system, seamlessly without having to switch it and turn it down.
Since you use the term battery, I can put you on the spot then and ask battery question. So, we all know lithium-ion batteries, very popular. They do have a tendency to catch fire and wear out in times and things like that, right? So how does the Energy Vault compare? I mean, if I buy one, what's the lifetime of it? Does performance change or degrade over time? That type of thing.
So the actual battery, no, because the phase change material and the weight of phase change material stored is a physical fact, and that's not likely to degrade or wear out. The container is metal. I suppose if it receives good housekeeping, its lifespan can be 20 or 30 years. The battery charger, the lifespan can be anticipated to be equal at least to a water chiller, and then be repaired in a modular manner if it was required rather than replacement. So both sides, both the charger and the battery, have got great longevity. Unlike a lithium battery, you can completely discharge it. You can take it right down to 0 contents. You can charge it right up to 100%. There's no time limit on either end of that operation, and you don't get degradation of its thermal integrity through all its years of usage.
I think, as most people know, with lithium ion, after the 10-year life cycle, it's probably only going to deliver 70% of its duty. It also has a limited turnaround efficiency. So when we've calculated this, the life cycle comparison, as Bob was describing, a 20-year Energy Vault type system, is typically about 40% of the lifetime cost compared to the current lithium-ion battery prices. So it's first cost competitive, and its lifetime very, very cost competitive.
Like I said, and again, I'm sorry, I'm sorry, Chloe, we got so many questions coming in. This just is absolutely fantastic. So I'm sorry to interrupt.
No.
Person, how are repairs made? Do your techs need to come on site, or do you have trusted service providers?
Our rollout plan is to have technology partners everywhere there is a Energy Vault. For minor repair maintenance, on-site is ideal, but being modular built, I'm sure a model will develop where maintenance becomes a swap out.
Most of your maintenance would be on the charger anyway, and I'm assuming it would not be particularly difficult to find good technical partners and things like that from the refrigeration, industry as well, in general.
Yeah, absolutely. There is nothing particularly groundbreaking or difficult to maintain on the charger at all. It's an ammonia system fundamentally. We will consider other refrigerants, but with ammonia being zero DP and zero carbon, it would make sense to try and maintain it.
Yeah, so that seems relatively easy for the customer then. It looks like we might have another question soon, but in the meantime, I always like to ask, just from a different point of view, is there anything that maybe we haven't discussed yet that you think is important for people to understand about the development of the system, and maybe kind of where you guys see yourself in the future, or I guess just anything in general that you would want to share that maybe I didn't touch base on yet?
I had a couple down here that I thought may need prompting, but we've actually covered them. One was how does the battery charging take place, and we've discussed through AI or building management or a collaboration of the two. We've discussed the rapid charge and discharge. We're covering things well here.
That's great.
The one thing I would, I guess, add, and that's because I'm a finance guy, is what's the economic payback? What's the return on investment on an Energy Vault?
That's very true.
Because at the end of the day, plant operators will see the benefits of having a battery there and the protections and support it gives their chiller systems, but the finance people want to know whether it's a worthwhile investment.
Right.
There's not a simple, straightforward answer to that, because it depends how the customer wants to use it. But for a customer that, say, is wanting to load shift from daytime to nighttime, a bit of support with chiller optimization, and able to use some on-site solar, which is not an uncommon collection of customer characteristics, the payback's likely to be in the 3, maybe 4 year period. We have another customer that we're talking to in the UK. His payback is 1 day, which is it's a unique one, but again, it illustrates the functionality of Energy Vault. They have to shut down production if temperatures get above a certain ambient temperature, because their existing chillers cannot cope. Now, that's only for a few days a year, because the UK is that hot. But for a few days a year, they've got to shut down production, and shutting down production can cost them millions of pounds in lost revenue. By having an Energy Vault just to support that real peak demand, it pays for itself on 1 day shutdown. Now, I'm not expecting to have that at all, but there's a lot of variety. But for a reasonable site, 3 to 4 years is a realistic payback.
It's pretty fast, in my opinion.
That particular example is very interesting. And I'm sure climatically, you will have areas in the USA that suffer similarly. For 3 or 4 weeks of the year, the humidity rises annually. And the evaporative cooling towers that provide all the cooling for the factory are downgraded in capacity. So just to qualify that, if any of our listeners are thinking, well, why don't they just buy another water chiller and stick it on the end? It's not really as easy as that. The climatic conditions prevailing for this short period of time have the effect in downgrading the performance of just about all the refrigeration equipment that this site employs.
That's awesome. Yeah, while we were talking, actually, another question came up with regards to how you guys quote your customers, I guess, in terms of the process. There's people that were curious if you can quote via NDA and utility bills sharing, if they're located on the East Coast of the US.
One of the things that we've done quite a lot of actually in sort of dialogue with a number of potential customers is gain access to what in the UK is half-hourly energy data. So what we tend to do is, get a general indication of customers' cooling demand and their energy or commercial energy supply tariff rates and such like. Get an understanding whether energy vaults are fit and the general scale of it, and then essentially look for their half-hourly energy data and the BMS data, which shows the corresponding chiller duty against that site energy data. So we've got the duty cycles and the profiles of usage, and from that we have a series of models which basically allow us to model the business case, if you will. Now, obviously, we've done that in the UK. We've done some work in the US, and obviously, conversations with David have started this in a bit more detail. We shared some more detailed models which we've got. So we would typically put that sort of site-specific, customer-specific energy supply contract and chiller duty cycles into our models to understand what the sizing is and therefore what the business case is. That's generally the approach that we would take. If necessary, we might consider putting monitoring equipment on a particular site to understand better if that information doesn't exist and it's felt that would be valuable in quantifying and sizing systems. But generally, if we can get access to meter data, that metadata and BMS data, or anything that demonstrates the chiller duty cycle alongside the energy consumption, then that gives us a basis from which we can put a business case together.
Great, thanks, Jeff. As a concierge utility, if you want to reach out to us, we'll certainly make all of the necessary arrangements to get everything over to these gentlemen here and help you, navigate that process again, because we also provide the integration with the BMS as well as renewable energy and things like that. But that being said, what is the best way to contact you guys?
info@ohx.com. I guess. info@o-hx.com.
Awesome. And I'll go ahead and put that in the chat for everyone to see.
Yeah, if anybody goes to the OHX and it's getting to O-HX website, there's contact details on there as well. So you'll get through to us.
And please don't be frightened to ask any question whatsoever. Even if you may think it may sound stupid, we certainly won't. We have been asked everything by everyone.
I'm sure.
Mainly by me, because I'm not an engineer. I've asked all the stupid questions already.
I feel that. That's me. Well, does anyone else in the group have any additional questions? I know we had a few. But yeah, if anyone else, feel free to chime in.
Yeah, people are starting to say goodbye. There has been a unanimous thank you and applause for this technology. I really appreciate it. And I'm sure people will be reaching out to both you and us directly on this. Gentlemen, thank you so much. Chloe, also, thank you for hosting.
Thank you guys for
Thank you.
meeting
Thanks
with
for having
me.
us.
Thank you.
Thanks,
Thank you very
everyone.
much.
Take care.
Bye,
Grace.
guys.
Bye-bye.